right, guys, so we are starting our next unit. We are starting unit 6, which is going to be all about what are called rational functions. So in this first section, we're just going to introduce the idea of what a rational function is, as well as show some ways that we can simplify it. Before we get into rational functions, we're going to do just a couple quick review sessions. We're first going to review a little bit of factoring, and then we're going to review some rules of exponents. So with factoring, let's kind of review some of the major types of factoring that we can see. Starting with this first expression, x squared minus 4. We've got a difference. Anytime we see a difference in two terms, we should be thinking difference of squares. In fact, we do have a difference of squares. Both x squared and 4 are perfect squares. X squared is the term x being squared. 4 is the number 2 being squared. And then remember to put a plus and minus as your signs in between those terms. So your factors for x squared minus 4 would be x plus 2 and x minus 2. For our next expression, x squared plus 11x plus 28, notice that we have three terms. So we're going to try to do a more traditional type of factoring. In other words, we're going to try to find two numbers that multiply to be 28, which also add to be 11. Which shouldn't be too hard to find. The two numbers that are going to work are going to be 7 and 4. 7 multiplied by 4 is 28, and 7 plus 4 is 11. The only thing we have left to do is just put x plus each of those numbers since they're both positive, and we've got our two factors. So x plus 7 and x plus 4 would multiply to be x squared plus 11x plus 28. Now in this third expression, we're going to do something very similar. Notice that we have three terms once again. The difference is, notice that this time there's a GCF which we can factor out first. Notice that each of the terms has x in common. So let's factor out an x, which will leave us with x squared minus x minus 6 inside the parentheses. Now we're going to look for two numbers which multiply to be negative 6 and add to be negative 1. And with a little bit of trial and error, you can probably figure out that those two numbers are going to be negative 3 and positive 2. Once again, we're going to put x in front of each of those. For 2, since it's positive, we'll put x plus 2. And there's going to be our factors. So we're going to end up with 3 factors in this case, which should make sense since our degree was 3. The 3 factors being x, x minus 3, and x plus 2. Now this last expression is probably the trickiest. It is the one that takes a little bit more time, which is where you don't have a common factor and the number in front of x squared is a number larger than 1. In this case, we're going to start by taking that number in front of x squared and multiplying it by our constant. So 8 multiplied by negative 3 is a negative 24. We're then going to set up this x, or some people will call it a diamond, with the negative 24 on top and the negative 10 underneath. So now we're still looking for numbers that multiply to be negative 24. They also have to add to be negative 10. And in this case, those two numbers are going to have to be negative 12 and 2. Be careful trying to use negative 4 and negative 6. While negative 4 plus negative 6 is negative 10, it does multiply to be positive 24, not negative 24. Now we're not quite done yet. It'd be nice if we could just write x minus 12 and x plus 2 as our answers. However, we still need to use this 8, which we multiplied at the very beginning. In fact, what we're going to do is place that 8 above each of those numbers that we just found. So we're going to put 8 along with the negative 12, as well as 8 and positive 2. On each side of the x now, we're going to try to simplify our terms by taking out any common factors. On the left side with 8 and negative 12, those are both divisible by 4. 8 divided by 4 is 2. Negative 12 divided by 4 is negative 3. Doing that same process on the right side, 8 divided by 2, which is our common factor on this side, is 4, and 2 divided by 2 is 1. We're now ready to go ahead and write what our factors would be. Our first factor using the two numbers on the left side of our x is going to be 2x minus 3. Our second factor using the numbers on the right side is going to be 4x plus 1. So as we go into simplifying rationals a little bit later, it's going to be important to remember each of those types of factoring, as well as a few more that we've discussed before. If you need a little bit more review, you might want to go back to Unit 4, where we talked about factoring, to get a little bit more help with that. All right. In addition to remembering factoring, there are a couple of exponent rules that we will be using today, which will be helpful when we are simplifying. So to review, if you have x to the power of a multiplied by x to the power of b, in other words, you are multiplying with a common base. The base is the same for both, it's x. Then, the way that we simplify this is that we add our exponents together. In other words, we take x to the power of a plus b. Which, if you didn't remember that rule, you can use that rule to help us remember this next rule. So if you have x to the power of a over x to the power of b, think about what we did before. When we were multiplying, we added our exponents. So now when we're dividing, it would only make sense for us to subtract our exponents and take x to the power of a minus b. However, oftentimes when I work through using this rule, I do it a little bit differently. I look for where do I have more of a particular base, and then I keep that base there and simplify it as much as possible. We'll talk a little bit more about that as we look at some examples. Okay, so let's go ahead and define what a rational function is, or in this case today, what a rational expression is. So a rational expression is an expression which is the ratio of two polynomials. Which is why we need to study this after Unit 5, where we talked about polynomials, is we need to have an understanding of what a polynomial is before we can talk about rational functions, since rational functions are made up of polynomial functions. So let's talk about what we mean for a rational expression to be simplified. So we say that a rational expression is simplified if it contains only one of each base. And it might be helpful to think of bases as also being factors. So we say for a rational function to be simplified, it can only have one of each base or factor. So we're going to take a look at about 6 examples today, and then we'll see in later sections how we can use this to go through some of the basic operations, such as adding, subtracting, multiplying, and dividing, as well as how to solve and graph rational functions. So let's go ahead and take a look at some examples of simplifying first. So in this first example, we've got 12x squared y to the third over 18x to the fifth y. Now there are multiple variables, but technically these would still be considered to be polynomials. To simplify this, we're going to separate each of our different parts of our expression. In other words, the 12 and the 18 will be treated separately from the x squared and x to the fifth, which will be treated separately from y to the third and y. So let's look at the 12 and 18 first of all. If we were to simplify 12 and 18, they are both divisible by 6. 12 divided by 6 is 2. 18 divided by 6 is 3. So we're going to have 2 over 3 as part of our simplified fraction. For the next part, let's take a look at x. We've got x to the second power in our numerator and x to the fifth power. If you wanted to use the rules of exponents, you would take 2 minus 5, which is negative 3, and since it's negative, it would tell you to put x to the third in your denominator. But a more simple way to think about this might be to think about where do I have more of my x variable? And clearly there are more x's in my denominator. How many more? Well, 5 minus 2 tells me that I have 3 more in my denominator. That would mean that x to the third will remain in my denominator. So you can either use the rule or you can just simply think about where do you have more of a particular variable or factor. For our last variable y, we've got y to the third in our numerator, y to the first in our denominator. If we subtract, 3 minus 1 is positive 2. Since it's positive, we will put y to the second in our numerator. At this point, notice that all of our bases are only listed just once. We only have one x variable, we only have one y variable, and the numbers can no longer be simplified. That means that we are done simplifying. There is our final answer. All right, let's take a look at example B. So example B, a little bit different. We do have two polynomials. The first is 6x plus 4. The second is 3x plus 2. And while it might be tempting to want to do something similar and to draw in a bar and try to simplify this by saying 6x divided by 3x is 2, 4 divided by 2 is 2, and 2 multiplied by 2 is 4, or even 2 plus 2 is 4, and there would be our answer. But this is incorrect. Please, please, please do not ever try to simplify in this way. Instead, what we need to do is we need to rewrite our expressions so that they're being multiplied. Notice that everywhere I drew in a line to separate my terms on example A, there was multiplication in between each of my terms. So between the 12 and x squared is multiplication, between x squared and y to the third is multiplication. And while there is multiplication between the 6 and the x, there isn't multiplication between the x and the 4. So we really can't work this problem the same way that we did example A. Instead, what we're going to look to do is try to factor. So looking to factor both our numerator and denominator, in our numerator, we do have a greatest common factor which can be brought out. 6x plus 4 has a greatest common factor of 2. And what's left when you're done factoring that out is 3x plus 2. In our denominator, there is no greatest common factor. There is just the 3x plus 2, and it might be best to put that in parentheses. So now what's different is that we can treat this like our previous problem. Notice that between the 2 and the 3x plus 2, there is multiplication. And if you wanted to think about it, between the 3x plus 2, you could think of there being a 1 in front. There's multiplication there as well. And there is some stuff that we can actually do to simplify. Notice that 3x plus 2 can be divided out from both our numerator and denominator. What that leaves us with is 2 over 1, which just simplifies to be 2. There is our final answer for part B. Moving ahead, let's take a look at example C. So we've got 20x to the third, y to the fourth, over 4x, y to the fifth. Notice in this particular problem, they are all being multiplied together, so we can go ahead and separate those and go ahead and simplify each of the different parts. Starting with our numbers, we've got 20 and 4 which are both divisible by 4. 20 divided by 4 is 5, and 4 divided by 4 is 1. For our next variable for x, we have 3 x's in our numerator, just 1 in our denominator. That means that there are 2 more x's in our numerator, so that's going to be how we'll simplify. We'll do something similar with y. For y to the fourth over y to the fifth, there are more y's in our denominator. In fact, there's 1 more y in our denominator than our numerator. So we're just going to put y to the first power, or just y in our denominator. At which point, we can notice that we no longer need this 1 in front of y. And at this point, we can also notice that we only have 1 of each base, in which case we are done. All right. So let's take a look at a few more examples where we have a little bit more factoring to do. Obviously, A and C are a little bit different, where you've got multiple variables. What we are going to focus more on is examples like D, E, and F here. So taking a look at D, fortunately for us, it's already been factored. If there's never ever parentheses that are missing from a factor, like x plus 2 in our numerator, it would probably be best to think about that as being in parentheses. And once we've done that, we can notice that x plus 2 is a common factor which can be divided out of both our numerator and denominator. What that'll leave us with is x minus 5 in our denominator, and really nothing left in our numerator. However, think about dividing out a common factor. When you take something and divide it by itself, or think about what number that would have been in front of the parentheses, which is a 1, that 1 does need to go in our numerator in order to keep x minus 5 in our denominator. For our next example for e, once again, please be careful not to try to start simplifying like this, where x squared divided by x squared is 1, 49 divided by 7 is 7, and so on. Because notice, once again, you don't have multiplication. You must have multiplication in order to begin simplifying. So, in order to create multiplication, a common strategy that we will continue to use is that we're going to factor. Let's start by looking at our numerator, x squared minus 49. It's got two terms, it's got subtraction in the middle, which tells us that we should be looking for difference of squares. And in fact, x squared and 49 are perfect squares. If we were to factor that then, x squared would be x multiplied by x, 49 would be 7 multiplied by itself, and we just need to make sure that 1 is plus and 1 is minus. As for our denominator, we've got three terms, which tells us we need to start thinking about what numbers multiply to be our constant 7 and also add to be our middle coefficient, which is negative 8. And those two numbers are going to be negative 1 and negative 7. So negative 7 and negative 1 clearly multiply to be 7. They also add to be negative 8. We just need to put x in front of both of those, and now we've got our two factors. Now, notice that by factoring, you create multiplication. There's now multiplication between x plus 7 and x minus 7. There's also multiplication between x minus 7 and x minus 1. So now we look for common factors which we can divide from both our numerator and denominator. And there is actually a common factor. X minus 7 can be divided from both our numerator and denominator. Now, even though it's not directly above one another, we can still simplify it like this. That leaves us with x plus 7 in our numerator and x minus 1 in our denominator, and in fact, that is going to be our final answer. Finally, for f, we're going to look at x squared plus 3x plus 2 over x squared minus 4. Once again, since there is not multiplication right away, we're going to look to factor and create that multiplication. So with our numerator being three terms, we're going to look for numbers that multiply to be 2, that add to be positive 3, which it looks like the two numbers that would work would be x plus 1 and x plus 2. As for our denominator, x squared minus 4, we've already factored this. In fact, this was our warm-up example. But notice that it is also a difference of squares. So our two factors are going to be x plus 2 and x minus 2. At this point, we're going to simplify anything that we can. So x plus 2 is going to be factored from each of our terms in both our numerator and denominator. That leaves us with a final answer of x plus 1 over x minus 2. Now, in addition to each of these particular examples, we were also asked to state any domain restrictions. What we mean by domain restrictions is that there are certain numbers that x cannot be equal to, especially when dividing, because of the fact that there's a single number that you cannot divide by. Remember that dividing by 0 is undefined. We're not able to divide by 0. So anything that would make our denominator equal 0 is a problem. So let's go through each of these examples and talk about what would make our denominator 0. Looking at our original expression, for example A, we have x and y both in our denominator. If x were equal to 0, then obviously our denominator would equal 0, and that's going to be a problem. So we're going to say that x cannot equal 0. The same thing with y. If you notice, y cannot equal 0 as well. If y were to equal 0, then you'd have 0 right here, and then that would make the rest of your denominator 0, which would be a problem. Now, one of those domain restrictions is still visible in your expression. Notice that you still have x in your denominator for your final answer, so it should already be noted that x cannot equal 0 is kind of already implied, that we already understand x cannot equal 0. The one that's more important is that y cannot equal 0, because we can no longer see that when we write our final answer. In fact, this is the domain restriction that you'll want to use for big ideas math when you're working through the homework. X cannot equal 0 should still be treated as a domain restriction. However, big ideas will not need for you to write that as one of the restrictions. Let's do the same thing for example B. So example B, we have 3x plus 2 in our denominator. So what we need to figure out is what would make that equal 0. And in solving for x, we'll find out that if x were equal to negative 2/3, then that would be a problem. That would mean our denominator would equal 0, and we would have a problem with dividing by 0. So once again, we're going to say x cannot equal negative 2/3. Looking at our final answer, there is no variables in our denominator, so we do need to actually list this on Big Ideas Math as a restriction. Let's take a look at C. So in example C, notice that again, when we started the problem, we had both x and y in our denominator, so we need to make sure that both of those are not equal to 0. Looking at our final answer, y is still in our denominator, so the y cannot equal 0 should still be implied by looking at that. However, we can no longer see that x cannot equal 0. That's going to be the answer which Big Ideas will want for you to use as your domain restriction, since there's no longer an x somewhere in your denominator. All right, taking a look at example D. There would be two numbers looking at your factors that would make your denominator 0. We don't want for x to be negative 2 because then our first factor would be equal to 0. We also do not want for x to be equal to 5 because then our second factor would be equal to 0. One of those two factors is still in our final answer. Notice that x minus 5 is still there, which means that we can still see pretty clearly that x can equal 5. The one that is not clearly seen anymore is the negative 2. That's once again the answer that Big Ideas Math will want for the domain restriction. For example E, we once again had two factors in our denominator, x minus 7 and x minus 1, which means that we don't want for x to be equal to 7 and we don't want for x to be equal to 1. In either case, one of our two factors would equal 0. One of those is still apparent in our final answer. Notice that x minus 1 is still part of our denominator, so it should be pretty clear that x can equal 1 still. However, we can no longer see that x cannot equal 7. So once again, that's going to be the answer that you'll want to use on Big Ideas Math. Finally, for example F, there were once again two factors in our denominator, which means that we cannot have x equal negative 2 because then our first factor would be equal to 0. We also cannot have x equal to positive 2 because then our second factor would equal 0. Once again, looking at our final answer, x minus 2 is still in our denominator, so it should be pretty clear still that x cannot equal 2. However, we can no longer see that x cannot equal negative 2. That's going to be once again the answer on Big Ideas Math. All right, that is it for today's notes. In the next section, we'll take a look at multiplying and dividing, which is really merely an extension of simplifying and what we looked at today. Until then, have a great rest of your day.